Welcome to the next video in the Discrete Math video series, and here we are going to be showing the solution, which is the truth table for this particular proposition. So over here is my production of the truth table. At the end of the day, I think as long as I did it right and you did it right, then the values right here are really what you need to worry about. And so if you want to just quickly check your solution, then just check that you've got the same values right there. That is probably enough. To generate them, I'll just do another walkthrough of how I like to do these tables. So I transcribe the values of A, so T's halfway down, F the rest of the way. B always goes 2 T's, 2 F's, well, you know, when there are this many variables and so on and so on. But yeah, there you go. There's a transcription of all the B values. My C goes true, false, true, false. And then let's do the first logical operator that we can, that is able to be computed at this stage. And here that means this negation, right? This is the next one that could be computed, right? This disjunction cannot be computed yet because it needs the values that come from here. Well, that one also cannot be computed yet because it needs the values that come from here. So, okay. But we can compute the negation. So let's do that. We just toggle trues to false and vice versa. Now we can compute this conjunction because we can read the the values from the left and from the right. So here my rule for conjunction is to look for rows where there is true on both sides. So I guess here's a true on both sides, here's a true on both sides. But nowhere else is a true on both sides, so I can fill in every other row with false. And now I am ready to look at the disjunction, reading from the conjunction on the left and the C on the right. And so here for disjunction, I look for double false. So double false occurs on this one, right, coming from these two false values. And where else? Here, I suppose, is another double false, right, coming from here and here. So I go ahead and fill in that false value. And there is no other double false, right, on the left and on the right, so everything else gets filled in with true. And here you have the table produced. Okay, cool. Let's continue to the next topic. So, conditional sentences, very, very important. It is yet another binary operator. This one is arguably the most important, possibly, right? I mean, I guess there's an argument for it. There's also an argument that they're all equally important, but whatever. Anyway. It is meant to represent the phrase if P then Q. This is called a conditional or an implication. And the symbol that we write to join if P then Q is P right arrow Q. And we can say, well, it is false in precisely one case. I'll point down here to the truth table, but this is also the same as what I have written out long form right there. And so it is false when P is, I have that backwards. How did I make that mistake? Well, my apologies, but in the notes, this should be that it is false when P is true and Q is false. And so that's this right here. And and in every other case, it is true. So there's your truth table. That's a conditional. I guess, here what we want to point out is that, we're trying to at least have some amount of a correspondence between our formal logical system and natural English language, but that match is not always a great match. A lot of, here we're basically analyzing things in a truth functional way, right? We imagine that there is some component sentence that has a true or a false value, and it builds up by way of operations and through rules, simple truth rules for the truth values of the component sentences, you can build up the truth value of the final sentence. Well, there's a lot of English language that just doesn't work that way. And so one way to see this is you could, think about the sentence, either you're in or you're out, right? And we know that what that kind of means is that it's more like an ultimatum or something like that. It's maybe even a threat or something, but it doesn't communicate nothing. But if we formalize that with logic, I mean, that is essentially saying, if P is the sentence you're in negation P, right? If you're not in, then you're out, then it's effectively telling you nothing, right? It's saying basically P or not P, which is so trivially uninformative as to be not worth saying. So from a pure logic perspective, this is how you would communicate it. And then if you communicated that, you would have communicated nothing. So clearly with natural English, there's just like this not perfect match between what we say and what it somewhat sort of formally communicates versus what it really effectively communicates. So anyway, let's get into this next exercise. So let's find out, right, and by the way, the point of bringing this up now, right, this whole conversation about how, the formal logical system doesn't always match the natural language system in perfect ways, is that this mismatch gets especially pronounced with conditional sentences. And so you're going to find that, like, as you think about these sentences, what you would naturally say is probably not often what the formal system determines is the truth value of these sentences. But so, yeah, go ahead and determine the truth values of these sentences. Of course, this is a false sentence, and the sun is cold is a false sentence. And so on, right? This is a true sentence and so on. And so using the rules for true and false sentences that we have given for conditional propositions, go ahead and determine the truth values of these propositions.